Hello guys, welcome to my final draft of my presentation for the integer zero. So throughout the presentation we hope to answer questions about where zero came to be, what a zero represents, and different cases where zero is used in math that we see today. So let us start by first introducing where our integer zero first came to be, because I'm pretty sure in one point in everybody's lives that we all thought, like, where did this number came from? Because it is such a weird number. Because zero was meant to represent nothing, and how can we think of nothing being a number? So let us dig into it. The first civilization that we have studied and found that uh, they had a concept of zero was the Sumerian civilization, which were located in Mesopotamia about 4,000 years ago. And what they did was they used zero as a placeholder so they can represent larger numbers in their number system. So an example would be, for us, would be 205. We use zero to indicate that there's no value in that place. So we were able to, so instead of us thinking of 205 as 25, that zero helps us represent it as a much bigger number, which would be 205. So the next civilization that we see that also had a concept for zero were the Babylonians. And they came about a couple of thousand years after the Sumerians, but it is actually thought that the Sumerians passed down their knowledge to the Babylonians, which is why they had this concept of zero to begin with. So, uh, in addition, the Babylonians were able to improve on this concept of zero, because the Sumerians, when they first thought of it, they just left a space to indicate that placeholder, so it would just be a space in between numbers, and it was very easy to misinterpret, because without context, one space may look like two spaces, and two spaces may look like one space or three spaces, so it was very easy to misinterpret. So the Babylonians, what they did was they created a symbol to represent zero instead of just leaving it as a space. So their symbol looked like two wedges that were slanted. So it was kind of like this, but with two lines. And this actually helped them to not misinterpret numbers, and it really helped. The next civilization that actually had the same concept of zero was the Mayans, which they developed it around 350 AD. And the cool thing about this was that since the Mayans were on the other side of the world, they actually came up with this concept of zero all by themselves without any help from other colonies or civilizations. And the cool thing about this is that they also thought of using zero or representing zero with the symbol, and their symbol was actually it kind of looked like the side view of a turtle. So imagine like holding a turtle and like turning it to the side, it would be like that shell side view. And yeah, this was actually cool, and I thought it was very fascinating, because the Mayans also thought of using it as a placeholder, and that's pretty much like the only ways these civilizations used it. But now that we get into the Hindu Arabs in the 7th century, they were the ones that actually were able to expand on this idea of zero by creating it as an integer. Now we're going to dive into our next subject of the presentation, which is zero's usage in mathematics. So our first section is zero's usage in exponents and powers. So what if I pose this question to you? What is anything to the power of zero? Well, many of you might already know that anything to the power of 0 is equal to 1. But how did we come up with this? Like, how did we know that this works? So here we will show actually why this works. First, before we do that though, we're gonna want to introduce refresh our memory about some rules for exponents. So our first rule is our product rule, which is pretty much when if we have the same base and we multiply them, and we multiply the two numbers, we can add the exponents. For the quotient rule, if we're dividing two numbers with the same base and different or the same exponents, we're able to subtract the exponents and keep the base. And for our negative rule is when anything to the power of a negative exponent, we can just flip it. So instead of it being x to the power of -1, it would be 1 over x to the power of +1, because that's what the negative does. It flips our value. So now that we know these rules and we have refreshed our memory, we can dive into actually how anything to the power of 0 equals 1. So let's do that. So our first rule is actually going to be using the fact that we know that one number subtracted by the same number gives us 0, we can rewrite our value of anything to the power of 0 as, for example, x to the 1 minus 1, because that also represents 0. So this is the same thing and we are not changing it. So now using that fact from step 1, we can dive into step 2, which is our negative power rule. So because of the fact that we can separate the exponents by having x to the power of 1 times x to the power of -1, we can actually now use our negative power rule to flip one of the x's. So that is going to get us into our third rule, which is quotient rule for exponents. Now that we have x over x, using the quotient rule for exponents, we can now simplify that to get our value of 1, because the numerator and the denominator are the same since they are both x to the power of 1. So thus we can simplify and getting that x to the power of 0 equals 1. So now, what if I asked you what is 0 to the power of 0? What is that equal to? Naturally, most people will say that it equals 0, because how can nothing to the power of nothing result in 1? But after we have just shown that anything to the power of 0 is equal to 1, doesn't that kind of make you reconsider your answer? So I'm actually going to prove this to you. This proof is not very well accepted, so take it with a grain of salt, but I just thought it was very cool and I just wanted to show it in this video. But most people would say that 0 to the power of 0 is actually undefined, so yeah. But let's dive into this. So to determine what 0 to the power of 0 is, we can use our handy dandy calculator and actually pick values that are really close to 0 to the power of 0. So for instance, we can do 1 to the power of 1, which is obviously 1. But what if we get 0.5 to the power of 0.5? Well, as we can see, it's actually lower than 1, so what if it starts decreasing? But as we can see, as we put more values into our calculator, we can see the closer and closer that we get to 0, the more our answer starts to represent the value of 1. Thus showing that 0 to the power of 0 is actually 1. But as I said before, many people will speculate that it's actually undefined, so take this with a grain of salt. Our next subject for our value of 0 is actually its usage in algebra. So let's dive into that. So when using zero in algebra, we typically set our function equal to zero, and doing this will allow us to find the roots or the solution to our function. And we usually do this when dealing with polynomials or trigonometric functions. And an example is this image here on the slide. So these roots represent when our curve or our function crosses our x-axis, because that is what our zero is representing. And this can show us a lot of different things in mathematics. So how do we solve for zero when dealing with polynomials? So this is very we learned this in algebra, like in high school algebra. So I'm not going to dive too deep into this because I want to dive more into the next subject of the presentation. So real quickly, to solve for polynomials that are equal to zero, we usually use the quadratic formula if it is a second degree polynomial. And if we are dealing with larger degree polynomials, we will most likely use the rational root theorem, and then check all possible values until we get one that works. And then after that, we would want to use long division for functions to pretty much find another polynomial. And then we keep doing that until we get a quadratic. So we can either factor or use a quadratic formula to solve for that degree polynomial that is greater than degree 2. So yeah, that's basically the majority of zero's usage in algebra. And our next section is actually one that I'm very excited for. It is the L'Hopital's rule. So zero is used in the L'Hopital's rule because zero is actually an indeterminate form if it is put as a fraction. So 0 over 0 is actually an indeterminate form. Another form that is indeterminate is infinity over infinity, and there's other ones, but for this presentation, we're going to be focusing mainly on our 0 over 0 indeterminate form. So using L'Hopital's rule, we find the limit of a function that results in one of these indeterminate forms. So an example here is as the limit of x goes to 4 of the function x to the third minus 64 all over x to the second minus 16. As we can see, if we plug in our value of 4 into x, we will result in our indeterminate form 0 over 0, which is not good because usually this means it's undefined. So how do we solve this problem? We will solve it by using L'Hopital's rule. And we do this. Well, before we do that, how does L'Hopital's rule work? Like, how did it come to be? So we're first going to show how it works, and then we'll come back and solve this question for you guys. So first we must understand how L'Hopital's rule works before we actually start using it, because what's the point of using it if you don't know how it works? So the theorem of L'Hopital's rule is actually verbatim, as I would state verbatim. If the limit of f of x over g of x is indeterminate, then the limit can be obtained by evaluating the limit of the quotient of the derivatives of f and g, or f of x over f of g. Therefore, we get that the limit of x as x approaches a of f of x over g of x equals the limit as x goes to a of f prime of x over g prime of x. So pretty much what this theorem is saying is that if our limit as x approaches a of f of x over g of x is an indeterminate form, so if it equals 0 over 0, then if we take the derivative of both f of x and g of x separately and plug it back in, then we will get an actual answer that is not in indeterminate form. So, we will now prove why this works. Our proof starts with consider the limit as x approaches a. So our limit is going to be the limit of x as x approaches a of f of x over g of x equals 0 over 0. As we can see, if we subtract the top and bottom by 0, it would not change our answer at all, because it would still result in an indeterminate form, thus proving that we can do this next step. So now we can change it again, because if we plug in f of a and g of a as our zeros, then if we plug in a to this bottom function right here, we will still get an indeterminate form, which will be 0 over 0. So this step also works because it does not change our answer. So now for our next step, we are going to actually divide the top and the bottom both by x minus a. And we are able to do this because using rules of quotients, we can flip the bottom one. So we would have f of x minus f of a over x minus a multiplied by x minus a all over g of x minus g of a, which would give us our original function that we had up here, which is the f of x minus f of a over g of x minus g of a, which is still an indeterminate form. Thus, we can do this next step. And as we can see, we can move the limits to each of our rational functions because they're separated. And then now, as we do this, we can see that the top of it, the numerator, is actually the formula for a derivative, and the denominator is the formula for the derivative of g of x. So, as we can see that we are slowly transforming our limit and our function into the derivative without changing our outcome, without changing that it still results in an indeterminate form. So now our last step is that we plug this all together, and then we finally get that the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. And we were able to do this without changing the outcome of our answer. So this shows that they are both the same. So if we do the derivative of f of x and g of x, plug it back into the function, then whatever answer we get from that will be the exact same answer we would get from our original limit. So now let us go back to our example, and we will show how this works on an actual function. So now, as we've seen before, if we plugged 4 in for x, we would get an indeterminate form. So now let us take the derivative of f of x, which is x to the third power minus 64, which in turn will be f prime of x equals 3x to the power of 2. Now that we did that, let's separately do the derivative of our value of g of x, or our function of g of x, which is x squared minus 16. And if we take the derivative, we will get g prime of x equals 2x. Thus, we can plug those back into our limit, and our function will be, or our limit would be, the limit of x as it approaches 4 of the function 3x to the power of 2 all over 2x. Now, as we can see, if we plug in our value of 4, it will not result in an indeterminate form. Thus, let us do so, and as we can see, we get the answer 6. So now we can say that our original limit, the limit as x approaches 4, x approaches 4 of the function x to the power of 3 minus 64 all over x to the power of 2 minus 16, we can say that that equals 6 because, as we shown in the proof, the limit of our original function is the same thing as the limit of the derivative of that function. So now, for the next part of our video, we will dive into zero's usage in computer science, which is actually very impressive and amazing. And I hope you guys enjoy this part. Okay, so without the value of 0, we would not have any computers or electronics at all, because zeros and ones are used as the universal language that is called binary coding. So binary coding is used in a lot of computers and electronics and processors, and what it actually is a combination of using the numbers ones and zeros to represent different letters and numbers, and like with this, we are able to combine sequences of these different combinations of ones and zeros, and from this we're able to build code, we're able to build coding, we're able to build processors, we're able to there's a lot of different things you're able to do with this. And one of the most popular ones that is used today in almost every electronic is 8-bit coding. So what 8-bit coding is, it is actually limiting our ones and zeros to 8 spaces. So imagine we have 8 empty spaces, and we have to fill up each space with ones and zeros. So why this is used frequently is because it was used in a lot of older electronics, and then they kind of just expanded on it. So what this 8-bit coding allows us to do is have 256 different possibilities of different numbers and different letters. Like it's a lot of possibilities. So now let us kind of get into our 8-bit coding and actually how we are able to read these binary numbers, because it is possible. Not only computers can read them, but humans can also. It might take a little longer for humans, but that's because computers have all the shortcuts. Okay, so now, how do these certain sequences make up letters and numbers? And when do these computers know whether to code them as either letters or numbers in certain cases? We will answer these questions throughout this part of the section on binary coding and computer science. So to decode 8-bit coding, it is actually not that hard. One way to think of it is to think of it as a base 2 system. And the base 2 system is not that different from our base 10 system. So our base 10 system, we have 10 numbers, and once we go through those 10 numbers, we pretty much repeat those numbers again, and then we do it again. With the base 2 system, it works the same way. So with this, we're able to use this little table that I made. So as we can see, this is an 8-bit code because there's 8 spaces of ones and zeros. And pretty much what we are going to do is we're going to decode this binary code to figure out what number it is. So our first step is to look at the digit all the way to the right. So our first digit is 0. So since we're in base 2, we're going to multiply 0 by 2 to the power of 0, because that is our first digit. And as a result, we're going to get 0. Next is our value of 1, which is in the next space, which is our next digit. In this one, we are going to multiply it to 2 to the power of 1. So 2 to the power of 1 times 1 equals 2. And then the next step, we're going to continue this step, and as we can see, we get 128 all the way to the left, plus 0, plus 32 plus 0 again plus 8 plus 0 again plus 2 and then plus 0 again. And now that we have this, we are able to add all of them up. And as we can see, our binary code 10101010 is actually the value of 107 in 8-bit coding. That was a lot just to find out one number, right? One value. So just imagine how complicated these codes can get, especially when you are designing something and you are giving it commands to, I don't know, pick up a juice or to walk or something, to pick something up. It gets very complicated, and here is a table of actually how you can write these binary codes in capital letters, lowercase letters, different symbols, and also our regular numbers that we know. So as we can see, just imagine writing a sentence with all these different binary codes. So imagine how you would have page lengths longs of just ones and zeros if you are writing even one sentence, because every letter consists of eight numbers of different combinations of ones and zeros. So yeah, this gets very complex, and this is mostly why we use this as a universal language, because this is how computers and processors talk. This is their language, and yeah, I just found it very fascinating, and I'm glad I was able to share it with you guys in this video. So now, sadly, this is the end of my presentation for the value of 0. These are my references that I used throughout the presentation. Thank you for watching, and I hope you guys enjoyed my presentation of the value of 0 and how fascinating it is, and when you apply it to math, and also when you apply it to computer science, especially because without the value of 0, we would not have all these appliances and electronics that we have today. So yeah, thank you guys, and I hope you guys have a good winter break.